Hi everyone, I'm Soumitri Chattopadhyay of the Department of Computer Science, UNC Chapel Hill, and I shall be presenting our work, Active Learning for Fine-Grained Sketch-Based Image Retrieval, accepted at BMVC 2023. I also have my co-author Himanshu Thakur, who is from the Carnegie Mellon University as the first author, and both authors contributed equally to this paper. So before getting into the details, let's first understand the task we are trying to solve. So our task is sketch-based image retrieval. So basically we have sketch as a query and we have a gallery of photos and we want to retrieve the photo which matches the sketch. So the recent focus has shifted from a class level or category level SBIR to a more fine-grained setup, that is instance level SBIR, where each sketch is corresponding to exactly one photo in the gallery. So basically we need is one sketch is to one photo correspondence, and drawing these faithful sketches for this sort of pairing to construct a data set is a pretty challenging and arduous task. It requires skill, and if you do not have proper sketches, the model would end up learning noisy sketches. And so this has led to the development of some annotation efficient techniques for FGSBIR. However, they are mostly computationally inefficient. One of the solutions is active learning for this annotation efficiency, and this has not been attempted before in this domain. And one of the reasons is that off-the-shelf active learning methods, which are proposed for classification like tasks, they are not really suitable for a cross-modal retrieval task because these methods usually draw rigid decision boundaries, while a fine-grained SBIR task requires soft decision boundaries. And secondly, a cross-modal retrieval task requires a cross-modal embedding space, which is learned, for example, photo and sketch. And so sampling for active learning requires handling of both photo and sketch modalities. So in this work, we propose a novel sampling technique for active learning that sort of utilizes the relation between photos and their sketches to measure the influence of a new photo that is being added to the existing learned embedding space. So our sampling technique is informed by the embedding space, its representation, and the influence a new element can exert on the learned embedding space. So we propose a metric called the violation index, which quantifies the degree of disturbance an image from the unlabeled pool produces in an existing embedding space while it is introduced using an active learning round. So we have like the violation index basically sort of measures the disturbance or the perturbation that is incurred in the existing embedding space when we try to introduce a new photo to it. And as you can see from the diagram, this is pretty intuitive to understand, and it is also formally defined in the equations given below. For the selection strategy, there usually exists a trade-off between reducing uncertainty and learning novel instances when they're being introduced. And to balance these counterintuitive effects, we consider using the advantage of both these paradigms, that is using both minimum violating or lower violation index values and also using higher violation index valued samples. And we use a hyperparameter to mix these two different types of samples to get the best out of both worlds. For the experiments, we have used mostly conventional data sets like Chair V2 and Shoe V2, and we have provided the training and testing splits. The implementation is based on the gold standard triplet model that is being trained with the triplet loss for fine-grained sketch-based image retrieval with the VGG encoder. We have considered 5 active learning cycles using state-of-the-art papers as the reference, and we have the evaluation metric as the top 1 and top 10 retrieval scores. So for the comparison, as we discussed that active learning cannot be adopted directly off the shelf. So we used some fundamental active learning strategies like core sets and k-means as the adopted baselines used on top of our fine-grained SBIR model. And one thing to note that our proposed active learning method requires no additional loss function or an external optimization paradigm. And it is just like a plug and play module on the existing SBIR model. and it can be used for increasing the data efficiency in each cycle of itself. So we see that our method outperforms the baselines on both of the data sets and obtains consistently higher accuracies. And we also achieve comparable performance to the state of the art technique by utilizing only 40 to 50% of the data set. As for ablations, we studied the significance of this VI and the diversity-based sampling, that is use of k-means plus plus. So we see that selecting minimum violating samples in the earlier stages performs better compared to maximum violating, because we can hypothesize that less training data requires more diversity among the samples. However, with increasing training data, we need to reduce the model uncertainty on these newly added samples. And also we see that diverse clusters obtained by k-means plus plus outperforms the vanilla VI baseline. We also perform a study on the hyperparameter alpha, and we observe that as we increase alpha from 0 to 1, there is a sudden drop in performance in the beginning, but we observe a steady increase with the top 1 retrieval scores. And this investigation is left for future investigations in the future. So in conclusion, for the first time, we propose an active learning framework to tackle annotation bottleneck in an instance-level cross-modal retrieval setup like fine-grained SBIR. And we do so by introducing a violation index, a metric that quantifies the latent space perturbation due to addition of a new instance. And we showed the robustness of our proposition in low data regimes, like 40 to 50% of the data set. And two advantages of our method is that our method can be used like a plug and play module to any fine-grained SBIR architecture or any cross-modal retrieval architecture, just to improve their performance or to make them data efficient. And furthermore, our approach is modality agnostic. So this can be leveraged for any instance level cross-modal retrieval task like audio-visual retrieval, text-to-video retrieval, and text-to-image retrieval. So thanks for watching, and hope we have a good